Thank you very much indeed, and welcome to everybody to the BAA Autumn webinar. This is obviously to replace the face-to-face meeting in Leeds, so thank you for dialing in, also for logging in. Before we start on the formal part, can I perhaps raise the awareness for one particular item, which is an all-party group which has been set up to relate to dark skies. It's been set up by the Astronomer Royal and also by Andrew Griffin, the MP for Arundel and South Downs, because South Downs is a dark sky area now, and they're setting up this all-party group and seeking basically feedback from organisations. The Commission for Dark Skies have already submitted their case. The BAA will be doing so. But it is also down at a personal level, both for you as individuals and also if you're involved with local astronomy societies. It's a huge opportunity for us to perhaps be able to influence political debate on this. So if details are in the newsletter, which was sent out, I believe, on Thursday, so if you had that, or you can look up the APBG Dark Skies on Google and get details of there. All submissions need to be in by the 27th of September. So with that, move on today's event. Unfortunately, Christine Dunn was unable to give her presentation today due to family issues, and I have to thank Professor Brad Gibson very much indeed for stepping in at short notice. So thanks very much indeed for that, Brad. If I read, Brad is the director of the A. Milne Centre for Astrophysics, and if I may just read this bit from your bio, Brad. His research led to the determination of the expansion rate of the universe with the HST Key project, the identification of the galactic habitable zone, for which National Geographic named his work one of the top 10 news stories of the year, and the discovery that our nearest galactic neighbours were being shredded by their interaction with the Milky Way. Brad is a passionate supporter of outreach schools and colleges and widening participation and diversity across all the STEM subjects. So without further ado, if I may, how the universe will end. Professor Brad Gibson, over to you, Brad. Thank you.
Thanks very much, Alan, and morning to everyone. I'd love to say that this is going to be an uplifting, thrilling talk, especially to start for what up here in Hull is a nice, sunny, beautiful day. But the reality is this is rather a dour, depressing one. The universe, as I'm going to show you, doesn't necessarily end in a spectacular, as this picture might show you here, cataclysmic event, but rather sort of the ends with a whimper, if you like. So what I'm going to do over the next 40 minutes or so is first take a little look backwards as to where we came from, where we are right now, and then I'll walk forward in time and we'll dip in a little bit at some of the high or low points that our universe and our planet, our solar system will encounter between now and the end of the universe. So, but before I sort of move forward in time, it's better to spend at least a couple of minutes looking backwards so we understand where we came from. This is probably one of the most used images in all of astronomy talks from NASA. And it sort of boils down the universe into this simple little cone diagram, starting from today over on the right with all the galaxies that we know and love that we can see today, and then looking backwards in time as we look towards the left, all the way back 13.7 billion years to the Big Bang. And I'm not going to go through it in gory details, but we can look back in time. We can do things like count the number of galaxies and the types of galaxies that we see as a function of look back time. We can use that information to infer the shape of the universe, the matter content of the universe, the age of the universe. We can use various metrics of things like exploding stars, supernova, to try to determine the expansion rate of the universe, which Alan mentioned in his intro was something that I worked on during my time in Colorado and Australia, determining what the present day expansion rate of the universe is. And you can get more subtle and work out the acceleration rates of the universe. But as we look back in time, let's go right back to the very beginning where we have the Big Bang. We have this singularity, this tiny little microscopic quantum soup with little quantum fluctuations. Ultimately, those quantum fluctuations, which are just, tiny, imperceptibly small, ultimately seed all of that structure that we see later in time and that we see today with our telescopes. But we go through whatever kicks off the Big Bang. Again, that's a whole other topic. It's way above my pay grade and more sort of mathematics than astronomy, if you like. But let's start 13.7 billion years ago. There is a Big Bang. There's a very rapid inflation of the universe. The universe is very hot, so hot and so dense at that point in time that all of the little fundamental particles called electrons that would normally be stuck to protons, which is what hydrogen is, just a positive charge proton and a negative charge electron. Helium is 2 protons, 2 neutrons, 2 electrons. In a nice, cold, normal universe, those electrons would be stuck to those atoms. But as the universe is so hot and so dense, the electrons get ripped off. And there's this sea of electrons, and all of the energy from the Big Bang is not really able to move very far. It gets bounced around by all of the electrons. But as the universe is rapidly inflating, getting bigger and bigger, it's cooling and cooling at the same time. And eventually, it cools enough, about a few 100,000 years after the Big Bang, it cools enough for those electrons to recombine onto the protons, onto the hydrogen and onto the helium. And it lifts this fog, this veil of electrons that's blocking the energy from the cosmic microwave background from moving very far. And we see that today as this mottled pattern of what is temperature. This is the entire sky. And the tiny little color differences that you see there reflect very tiny little temperature differences as you look from point to point to point to point across the sky. In this case, we see the energy of the cosmic microwave background today in terms of the photons that are left over, the energy from the Big Bang. If I take about a cubic centimeter of space right around me right now, there's about 300 photons from the Big Bang passing through that cubic centimeter right now. At the same time, there's about 3 million photons from the sun. But what that really means is that roughly 1 in 10,000 of the photons that are around you today are left over from the Big Bang. They're very low temperature, very low energy. A temperature now just a few degrees, but 2.7 degrees above what we call absolute zero, but minus 270 degrees Celsius, to do it in that scale. And so those temperature differences that you see from point to point to point, the little blue spots, the red spots, are regions of the sky where the temperature might be 2.7001 degrees or 2.6999 degrees. It's subtle temperature differences. But again, those subtle temperature differences reflect subtle differences in the density of the universe a few 100,000 years after the Big Bang. And those temperature differences ultimately seed the structure that we see today. And encoded within that mottled pattern, which may look more or less random to you, is really the secrets of the universe. Encoded in there is how large the universe is, what the shape of the universe is, what the matter content of the universe, how much dark matter is there, which you'll hear a lot more in subsequent talk from Dr. Andrea Font. How much mysterious dark energy there is. So the entire shape, age, structure, history of the universe up till today is encoded in that temperature pattern. And this is where we've learned an enormous amount of cosmology over the last 20, 30 years from using these sort of patterns in the sky. Now, again, this is probably something that Andrea will talk about in an hour or so. When we look at that pattern of temperature across the sky, if we look at how galaxies rotate, if we look at how the number of galaxies change as a function of time as we look back in redshift, we can take all of that information together, and it tells us that about 15% of the matter that we see around us today is normal. It's the stuff that you and I are made of, that our houses are made of. It's what we call baryons, the normal matter in the universe. The other 85% of the matter in the universe is the mysterious dark matter on which those normal baryons hang. And that's really what you'll be hearing about in the subsequent talk. We don't know exactly what that dark matter is. We can't pick it up and see it, but we can feel it. We can feel its gravitational influence on us, and we can see it in an indirect sense in that mottled pattern of temperature in the cosmic microwave background. So this is how we've learned, again, about what our universe is made of today, how old it is, how it's got to what we can see around us at this point in time. Now, here's where things start to get a little bit interesting. This is another way of looking at that history of the universe, taking that cone, but now just turning it vertical, if you like, with the Big Bang now at the bottom and today at the top. Now, I'm not going to spend a whole lot of time talking about the cosmology of the universe that we live in today, other than to say, you will hear the term a flat universe. And if you wanted to think of this in a sort of grossly, what this means is that if you could play God for a second and draw gigantic triangles across the universe, in a flat universe, those triangles would have nice straight sides. Or if you think back to maybe maths at GCSE level, if you added up all of the angles inside the triangle, it would add up to 180 degrees. If we lived in an open universe and could draw giant triangles across the universe, they would look like little pinched triangles. And if you added up the angles inside, it would be less than 180. In a closed universe, looks like this saddle here. If you added up the angles inside, it would be greater than 180 degrees inside that triangle. Now, if I look at this model of the universe from the Big Bang at the bottom, you can see as you move upwards, the cone starts to grow. And that reflects what I just talked about, the inflation of the universe, the rapid growth of the universe. And what you can see is that around sort of this point in the distant past, this might be 7, 8, 9, 10 billion years ago, let's say, instead of continuing to grow and grow and grow in size, you see it starts to get pinched a little bit. And that is the effect of dark matter. Dark matter, it's a strong gravitational influence, and the matter content of the universe at that point in time, 8, 9 billion years ago, is winning. So the universe is rapidly expanding, but gravity is trying to slow it down and pull it down. And so you can see it looks like the universe at that point in time has gone through a rapid expansion phase, and now maybe it's starting to close up again. But then what you notice is sort of 7, 8 billion years ago, that pinching stops, and it all of a sudden starts to flare back out again. And that reflects one of the great discoveries of the last 20, 25 years, and that is that we live in an accelerating universe. Something new happens to physics, and this new thing is dark energy. Dark energy starts to win out 7, 8 billion years ago over the dark matter, which is trying to close the universe, if you like, and the universe starts to go through a rapid expansion phase again, where it starts to accelerate rather than decelerate. Now, we live, like I said, in a flat universe. And if we were to look at where we are today, 13.7 billion years since the Big Bang, the universe is expanding, but not just expanding at a constant rate, which is the work that I did with the Hubble constant with the Hubble Space Telescope, but it's actually accelerating. So what that means is if we ignore sort of the random motions of stars and galaxies around us and just look at how fast the universe is expanding today, basically objects that are 1,000 light years away from us would be moving at, put it into units that we know and love, about 40 miles per hour. Objects that were 2,000 light years away from us would be moving at 80 miles per hour away from us. 3,000 light years away from us, 120 miles per hour away from us. And it's more than just a constant acceleration. Like I said, it's a constant expansion. It's actually accelerating. This rate is growing faster and faster as we move further and further away from us. And we're at this point now where dark energy, the influence of dark energy surpasses that of the dark matter. And these are two of the great fundamental mysteries in science, not just astronomy and astrophysics, is what is the nature of that dark energy and what is the nature of that dark matter. And so you're lucky to have Dr. Font talking after me, who will go into some of the gory details of both the dark matter and the dark energy. So that's just to give you a context of where our universe is today and what it's currently doing. To put some more common day events into this sort of timeline. Again, I will drop back and talk about some of these over the next half hour or so. This is another timeline, but maybe a timeline more relevant for us here on planet Earth, within our solar system, within our Milky Way galaxy. Here's us today. Again, Big Bang 13.7 billion years ago. The bulk, I would say the Milky Way and our sister galaxy, the Andromeda M31, the bulk of it formed 9, 10, 11, 12 billion years ago. There is still ongoing formation, that we are still accreting satellites, smaller satellites. Our galaxy is growing in terms of that accretion and cannibalizing of galaxies, as we say. There is ongoing star formation, but the bulk of the galaxy, the structure, its dark matter framework on which those baryons sit, formed in that 9 to 13 billion years ago. It passed. The solar system, the sun, we think of it, its age, 4.5, 5 billion years. The solar system formed over that window of 4.5, 6 billion years ago. Here on planet Earth, it took about 1 billion years or so for life to appear. Some debate as to the very first appearance of life. It didn't instantaneously appear once planet Earth formed, if you like. It's a pretty hostile, unpleasant, nasty environment while you're waiting for things to settle down, an atmosphere to develop, etc. So life has been around for about 3.5 billion years on planet Earth. If you look at things like mammals, they're very recent, about 200 million years, and us Homo sapiens, even more recent, but 200,000 years or so. So a lot of the life cycle, if you like, of this long timeline is compressed into a very small little window over here to the right, rather than spread over the entire timeline of the universe. And so as we start, we're going to start moving forward shortly, but it's actually pretty, in some sense, almost fortuitous, really, that we're even here to have this conversation, given the tiny little window of time in which, for example, Homo sapiens have been around, or the tiny window of time that mammals have been around. And there's a lot of things that we have had to navigate over the last 13.5 billion years to allow us to be sitting here having this conversation today. There are lots and lots of ways that we could have been wiped out. There's lots and lots of ways we could do it still today. That includes many things that we're probably worrying about a little bit right now, just in terms of pandemics, but more broadly, things related to societal self-destruction, if you like. And there's obviously, you can have an entire socio-political talk about the likelihood that we may be around, forgetting all the other potential physical things that could happen to us. How long can we survive in the current situation that we find ourselves right now? Would we still be here in 10,000 years, given the way we have treat ourselves and treat our planet over the last few decades? But again, that's a sort of a topic for another day. Let's just look at some of the astrophysical things that we have navigated over the recent past that we've managed to work our way through without getting wiped out. I won't spend a whole lot of time on it, but this is one of my favorite ones, is that every few 100 million years or so, we get jostled by spiral arms. So what does that mean? Again, if I could play God for a second and step out of the Milky Way galaxy and look down on it, this is what we would see: a grand design, classical spiral galaxy with beautiful spiral arms. We've got a bar in the center, supermassive black hole in the center. Our sun sits roughly halfway out, kind of in the suburbs. There are 100 billion stars in the disk. They're all moving around at roughly 500,000 miles per hour in nice, for the most part, circular orbits. And so we move along in a nice circular orbit, and we sit between two dense spiral arms where there's not, relatively speaking, a whole lot around us. And we're all moving in the same direction, the spiral arms and the sun. And where we sit, we are moving at roughly the same speed as the spiral arms. It's called co-rotation. The nice thing about that is you're kind of nestled between the spiral arms. There's not a whole lot to bother us as we move along in this nice circular orbit. But every few 100 million years or so, because we're not moving at exactly the same speed as the spiral arms, we actually catch up to the spiral arm and we pass through it relatively quickly. So we go from a region of space where there's not a whole lot around us to a region of space that might be 10 times denser. There's 10 times the amount of stuff in the spiral arms than there is in between the spiral arms. And so you race through a region where there's not a whole lot happening into the spiral arm where there is a whole lot of stuff around. And what that does is it gives you a short, sharp shock, not sort of the shock you would get when you stick your hand out from, you're driving in the car, there's air inside the car, there's air outside the car, you stick your hand out, you feel this shock, this pressure shock. It's a little bit different. It's similar in the sense that it is a shock, but it's gravity that causes the shock rather than a wind, if you like. But that's enough to shake up our solar system. Now, it doesn't bother our planets as we sit, the primary gravity that we feel that we are influenced by is that of the sun. The sort of gravitational shock that our planets get as we pass through the spiral arms is negligible, doesn't really have any effect on us whatsoever. But we always have to remember that our solar system is more than just the planets that we know and love. And if we were zooming out, here's our solar system up here. It fits in this, not that you'd be able to see it, probably this tiny little box right down in the center. Our solar system is much bigger. We're surrounded by this cloud of billions, possibly trillions of comets called the Oort cloud. They are also held on by gravity to our solar system, but because they are so far out, the gravitational influence is very, very weak. And so when we do get that gravitational shock of going through a spiral arm, again, our planets are oblivious, but those comets that are loosely held on by gravity, they get shook up and many of them will go flying away. They'll actually escape. They'll get enough energy that they'll escape the solar system, but many of them will get shaken up and come raining down into the inner part of the solar system. We know that this happens. We see it around other systems. We can look at the geological timeline of the Earth. We know that these things do happen. It's not a one-to-one correlation. Every single time you go through a spiral arm, this happens, but you do get that shock and comets do get shaken up, and it does happen. And all it takes is one of those large comets that's sort of the 10-mile, 20-mile, 30-mile diameter size to impact on you, that it starts to have a cataclysmic impact on us. The last time that this likely happened was about 65 million years ago, Cretaceous period, which took out the dinosaurs. But it also took out something between 70 and 80% of the species that existed on Earth at the time. Now, there have been, just in the last 500 million years, maybe 5 mass extinction events. They're not all down to comets or asteroids or meteors, large meteorites. That one is the Cretaceous. And so these things do happen. Now, again, we're still here to have this conversation. So it didn't actually wipe out all life. But again, if you were to interview the dinosaurs, they would say these sorts of events are very bad, and as well as the other 70, 80% of the species that were wiped out at the same time. So this is something that does happen. It doesn't happen so regularly for us because, like I said, we're moving at about the same speed as the spiral arms at co-rotation. If we were a little bit closer to the galactic center or a little bit further from the galactic center, we would run into the spiral arms a lot more regular than we do because we're at co-rotation. Whole other talk on the origins of life and what are the important astrophysical influences on it. This is likely one of the many important little pieces of the puzzle, being in a fairly sedate neighborhood where we don't get hit regularly by spiral arms. But this is one of the things that we have navigated, but it is something you do have to worry about because it is one of the ways that can wipe out life. And it's not just us, it does happen elsewhere. So many of us will remember about 25 years ago or so that comet Shoemaker-Levy impacted on Jupiter. So it's not just comets raining in and hitting Earth. We're actually a bit lucky that we have Jupiter sitting out there. It's kind of it's a big cometary Hoover in some sense. Again, probably one of the important little aspects of the development of life is having that cometary shield, if you like, further out from us. The Shoemaker-Levy was only about a mile or so in diameter. It wouldn't have been one of the ones that wiped us out completely, but it would have been if it had made it into the inner part of this solar system and had impacted on Earth, it would have had a devastating effect on us. And, for context, Shoemaker-Levy, again, it's about a mile or so across, so that's about 50 times larger in size than, for example, the Tunguska event in Siberia in the early 1900s. So these things do happen. They happen pretty regularly. We are fortunate that space is pretty empty, so most of these things do actually miss us. which is a good thing. But one thing, actually, I'll come back to that one in just 1 second. As we pass through the spiral arms, we also have to worry about, again, we're going from a region where there's not much around us into a region where there is a lot of stuff. And that includes young stars that are forming today. Most of the stars that form in the galaxy form in spiral arms. And those big stars, the ones that are 10, 20, 50 times heavier than the sun, they live fast, they die young spectacularly as a supernova, dumping out an enormous amount of energy, which is not a good thing if you happen to be very close to one. The best guess is that if you're within about 20 light years of an exploding star, that's sufficient energy as it washes across you to evaporate your biosphere. So again, these things don't happen every time we go through a spiral arm, but it does happen. And it actually was only about 10 million years ago that we were uncomfortably close to a star that exploded. It was about 100 light years away from us. So it was outside of the, if you like, the lethal radius zone that we talk about with supernova. But it was only, a factor of 5 or so further away. And you might ask, how do we know that this actually happened? It's because when stars like this explode, they create all, the positive, there are some negatives with an enormous amount of energy you have to worry about, but the positive is that everything you see around you today came from these sorts of stars, the oxygen, the magnesium, the silicon, the iron, et cetera, et cetera. One of the unique little tracers of an exploding star are weird little isotopes of chemical elements, radioactive isotopes, and one of them is called iron 60. It's just a trace isotope of iron, has roughly a 2 million year half-life. And our planet Earth is covered with this thin little layer of iron 60. And iron 60 only comes from these sorts of events, exploding stars. So this is exactly what happened 10 million years ago. Star was 100 light years away from us when it exploded. The wave passed over us, not enough to evaporate the biosphere, but it was enough to leave this thin layer of iron 60 spread across the surface of the Earth. It's a fascinating way to look at the fossil record of astrophysical events that have impacted on us in this case, not in a cataclysmic way, but precariously close to being potentially cataclysmic. And that was really only 10 million years ago, which is very short in the astronomical timeline that we've been talking about thus far. So that's sort of a very quick 10-minute walkthrough to where we are today, how old the universe is, what it's currently doing in terms of its expansion and acceleration. Now what I want to do is start winding the clock forward and look what's coming our way and what are the sorts of things that could potentially impact on us before we ever actually reach the end of the universe. So let's take a step forward in time. Again, I've picked out maybe a dozen things that have tickled my fancy. Some of them are potentially life-threatening. Some of them are just interesting and will be spectacular if we happen to be around during that period of time. So fairly recent, or not too far in the future, let's say 10,000 years from now, the star Antares, this is a star which is about 15 times the mass of the sun. Best guess is it's going to explode in that sort of time scale, about 10,000 years from now. Now it's 600 light years away, so it's much further than the 20 light years lethal radius zone of a supernova. So in that sense, we don't have to worry. But it still will be really spectacular. It'll be easily visible in the daylight. Other than the sun, it will be the brightest thing in the sky. So that will be a really exciting astronomical signpost, even though it's something that's not going to impact us in terms of our existence. Now, one that is potentially more problematic is you go forward in time 300,000 years from now. And there's this little star over here, zooming into it here. This is again a very massive star, so-called a Wolf-Rayet star. That's this unromantic name WR104. Best guess is it's going to explode on that sort of time scale, about 300,000 years from now. Now, it's quite far away from us, 7,000 light years. So again, far outside the 20 light year lethal radius zone. So it looks like we should be very safe. But this particular star, this Wolf-Rayet star, there's much debate in the literature about what type of exploding star this one will become. It looks like it won't be a standard exploding star, which are already pretty spectacular, but something that we call a potential gamma ray burst. Now, these are fairly rare events relative to exploding massive stars. They're a special type that are extremely energetic, maybe 100 times more energetic than the typical exploding supernova. And on top of it, so it's 100 times more powerful, but it's still 7,000 light years away. So again, that's far enough away that probably by itself, just by being more energetic, wouldn't be enough to wipe us out. But gamma ray bursts are a bit special. They take that enormous amount of energy and they funnel it into these jets, and that makes them a little bit more special. And what you don't want to, a safe zone, if a star explodes as a gamma ray burst and blasts out that enormous amount of energy in these jets, if you're off to the side of the jet when this explodes, that's fine. It's just like a normal exploding star. What you don't want to be is in the line of sight of one of these jets when it goes off. And the best guess, it got a lot of attention a couple of years ago. There were a number of press releases that came out saying that it looked like, from looking at the observations of this WR104, that it was spinning in a way so that its pole was pointed right towards us. And so when the star exploded and the jets came out through the poles, it looked like it was pointing more or less straight at us. And so again, there were a lot of press releases came out saying this was going to, this Death Star that was going to wipe us out. And it's possible. Now, over the last couple of years, there's been much debate in the astronomical literature about whether this thing really is pointed at us, the rotating pole of the star, or not, to the point that we don't really know whether when it explodes, the jets are going to be pointed towards us or away from us. If you just chose a random orientation, basically, if the jet is within 12 degrees of pointing towards us, so it doesn't have to be pointed straight at us, can be a little bit off, like plus or minus 12 degrees in any direction. If we happen to lie within that cone of 12 degrees, there's a very good chance that the energetics would evaporate our biosphere, and that would be it. Now, even just in a random sense, that's a 7% chance. So there's this 1 in 15 chance that this thing will be pointing at us. That's still better than 15 out of 15 times, but there, it's not non-negligible. It's this 1 in 15 chance that this star, if it does go off as a gamma ray burst as predicted, 1 in 15 chance that it will be pointed at us and we will be in that 12-degree cone of destruction, if you like. There has been some speculation that the mass extinction event sort of 500 million years ago towards the end of the Ordovician period was due to exactly this sort of event. Now, this is not sort of a unanimous acceptance across the literature. There are some who believe that is the case. There are many who believe it is something more geological rather than something that blasted us. But this is an ongoing area of research as we look for other isotopic patterns that you may be able to link back to an exploding star like a gamma ray burst, in the same way that we use that iron-60 thin layer tracer of a supernova explosion that covers the Earth. So if you're around in 300,000 years, you hope that we come down on the side of that 14 out of 15 times we will not be have that cone pointed straight at us. Now, if we come, this is, for me, one of the most interesting things I've learned over the last, I guess, 18 months or so. Like I said, as we pass through a spiral arm, that's every few 100 million years, we get a jostling, some comets get shaken loose. But you don't have to necessarily have the gravitational shock of a spiral arm shake you. There are other things that can shake our solar system and shake the Oort cloud. And this is one of them. This is almost a naked eye star, Gliese 710. It's about half the mass of the sun. But unlike the vast majority of the stars in our region, which are all moving at, like I said a few minutes ago, 500,000 miles per hour in a nice circular orbit around the Milky Way galaxy, this one is moving a little bit differently. It's moving at about 30,000 miles per hour, but it is coming straight towards us. It is like the barrel of a gun pointed right at us. I think it's 60, 70 light years away from us, something like that. But it is coming straight towards us. We've been monitoring it for a number of decades, and as we get better and better satellites up there that can measure the precise motion of the stars, it's only become more and more refined, and it is coming straight towards us. And at the distance it's at and the speed that it's moving, we know that in almost exactly 1 million years, this little star is actually going to pass through our solar system. Now, it's not going to pass down quite as close as the individual planets, but it's going to pass at a nice, slow, relatively slow speed right through the Oort cloud of comets. So that thing, this effectively a solar twin almost, within a factor of 2, is going to pass through a sea of comets, billions of comets, probably carrying its own sea of comets, its own Oort cloud as well. And as it passes through our solar system, the outer part of our solar system, there's going to be a strong gravitational influence on all of those comets. And again, many of the comets will get shaken loose and escape, but many of them will get shaken loose and come raining down to the inner part of the inner part of the solar system. And the best guess right now, oops, that didn't really work, is that for the subsequent million years after this star passes through our solar system, every month or so, a naked eye comet will appear in the sky. So the sky is going to be, over that sort of subsequent million-year period, again, space is mostly empty, so many of these comets, which are going to come raining down into the inner part of the solar system, potentially millions of them, they will likely miss us. But if you take 1 million comets and start throwing them into the inner part of the solar system over 1 million years, you do start to worry about the statistics and whether one of these comets is going to take us out. If you're interested in studying comets, it'll be a great time to be around in 1 million years from now, because the sky is going to be covered in comets. If you are interested in stars and galaxies, as a professional or amateur astronomer, the sky is going to be a lot less interesting, because you're going to basically have comets blocking your view. So, 6 of one, half a dozen of the other. This is just one way to represent it, just to show how graphic this really is. Now, there's about 100 stars on this plot. This is today. We've got a beautiful satellite up there in space now, Gaia, which measures very precisely the orbits of many, 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 many stars. And what we can do is, if we know how a star is moving precisely, we can wind the clock forward in time to see where it's going to be, and we can wind the clock backwards in time to see where it has been. And what we've done in this plot here is plot out for sort of 100 stars or so, the closest approach to our sun. And what you see is, on this scale, this is roughly about 3 light years. So, a few million years ago, the star was inside of, a bit closer, maybe a bit less than, a bit closer than, say, Proxima Centauri. But for the most part, they're all 3, 6, 9, 12 light years away from us at their closest approach, looking over sort of this plus or minus 10 million years. But you can see that little green dot there. That is this star, Gliese 710, that will actually pass right through the solar system. So this is going to be a spectacular time if you're someone who likes to study comets. If you're worried about the future of Earth, if I was going to point to one thing, at least in an astrophysical sense, that had the potential to wipe us out, this is the thing that will wipe us out before we ever get to sort of the end of the universe. Now, hopefully, in 1 million years' time, you'll probably still have Elon Musk around, who will have all kinds of wonderful equipment that will go out there and deflect it, or we'll have a disembodied Bruce Willis from Armageddon going up there and deflecting comets away from us with some cometary shield. But if we don't have that technology, this is likely the thing that potentially will take us out. It'll be, as I say, exciting times, but a bit scary as well. And we can start to sort of accelerate now a little bit forward in time. If we happen to get past the exploding Wolf-Rayet star, the gamma ray burst in a few 100,000 years, if we manage to avoid this rain of comets coming down on us in 1 million years' time, you do have to, statistically, these sorts of things do come along. We've seen, 65 million years ago, the last mass extinction event from the cometary impact. These things do happen on that sort of time scale. So you have to be prepared that this is going to come in a statistical sense. Some sort of mass extinction in an astrophysical sense will be coming along in that 100 million years or so. You can go forward 250 million years and just ask what would the Earth look like? It will be a lot different. The moon will have drifted away. It's moving away, a few centimeters a year. So in 250 million years, the moon will be 6,000 miles further away. So our day will be 25 hours rather than 24. We'll have completed our 20th circuit of the Milky Way, the solar system. But closer to home, the Earth will be very, very different. In only 50 million years, for example, Australia here will have rammed into Southeast Asia. And after this runs through to the end, it's a fascinating little simulation. After 250 million years, you will have effectively just one landmass that sort of wraps around the equator without really anything at the higher or lower latitudes. And you can see the Antarctic racing its way up as well. After a couple 100 million years, it also runs into this single landmass. So the Earth will look very, very different, even if we do happen to navigate these various things that we've talked about thus far. So it's just something to sort of bear in mind. And it's a whole fascinating topic is just looking at, for example, Australia, which is moving. In this accelerated movie, it looks like everything is moving quickly, but Australia really is moving very fast. As I said, it only took 50 million years to run into Southeast Asia, but it's moving at sort of a meter per decade. It doesn't sound like a whole lot, but it's enormous. It's a very fast moving plate, if you like. So fast, in fact, that things like, the standard way that we use GPS and sat nav doesn't work there. You have to have all kinds of extra things, corrections in place to take into account the fact that Australia is moving so fast. It's one of these little known things that we're not really aware of. And in fact, that the ability to do that GPS tracking and make those, allow you to use your Google Maps and sat nav when you're in Australia comes down to ultimately the fact that we are studying supermassive black holes on the other side of the universe. The International Celestial Reference Frame that all of those GPS satellites are anchored to. It's all based around a couple hundred supermassive black holes, a very distant universe. So our little world will look very different on this sort of time scale, even if we're still around. If you go forward just a little bit further in time to 500 million years from now, not only does the planet look very different in terms of having more or less a single continent, if you like, but stellar evolution, our sun will change in that 500 million years. It doesn't change a whole lot, but here's a plot which shows this is basically how bright the sun will be as a function of time relative to today. So here's us today with a value of 1. Now, L, the luminosity, the brightness, if you like. If I go forward just half a billion years, the sun is a little bit brighter. It's evolving. It's burning fuel, hydrogen into helium in its core through nuclear fusion. So that's changing its luminosity, its brightness a little bit. And so in half a billion years, it will be 5% brighter than it is today, which doesn't sound like a whole lot, but that 5% is enough to raise the average temperature on Earth from where it is now at sort of 20 degrees up to around 50 degrees or so. If you go forward in time about a billion years, the average temperature gets up to about 80 degrees centigrade. And again, most of the land by this point in time is all spread around the equator. There's not much at the poles. So even in half a billion years, 500 million years, the average temperature is going to be incredibly hot, very, very difficult, at least for life on the surface. Certainly in a billion years, very, very difficult. You can't simply move to the poles because there's no land there, but so you can start to envision sort of a Kevin Costner Waterworld thing where we're living up in the poles where it's a little bit cooler, or you go subterranean or underground. So the planet Earth will look to the eyes very, very different. And on that relatively short geological time scale, ignoring anything that we're doing to the planet Earth ourselves, just from a stellar evolution perspective, on that sort of time scale, 500 million to a billion years from now, you're talking about the surface going from 50 degrees centigrade to 80 degrees centigrade. So again, a very radical rethink would be required for life to be sustained on Earth at that point in time. Statistically, coming back to the statistics game, if we get past that Wolf Ray at 104, 300,000 years from now, the best guess is statistically a gamma ray burst will go off where the cone is pointing towards us on that sort of time scale. Now, how close it is sets whether it will be a completely cataclysmic event or just a minor one in the grand scheme of things. But again, we're just looking at a statistical perspective here, and so that's the sort of time scale when you might expect a gamma ray burst to go off that could potentially take out our biosphere. More tangibly, if we go forward in time now, 3 billion years from now, the moon again has continued its steady drift outwards. It's now 75,000 miles further away. That's far enough away that its gravitational influence starts to decline. So what that means is that, and it's one of the probably little pieces of the puzzle of the development of life, is the fact that we have this big heavy moon that we drag around us as it goes around us every month. It helps keep our what we call the obliquity stable. So our Earth is tilted 23 degrees away from the sun, but it stays 23 degrees away from the sun all the time, largely because we have this anchor that stabilizes it, and it keeps in a relatively sense, keeps our climate fairly stable. Now, as the moon drifts away, its gravitational influence goes down, and then Earth becomes more like a bowling ball as it goes around the sun. Not on that sort of time scale, but it does lead to much wilder climactic shifts, which again is not great for the development and the maintenance of life. And by this point in time, the sun will be 40% more luminous. The temperature will be 200-300 degrees Celsius. All water will have evaporated, and you get to the point where some of the rock now on the surface will be starting to melt. So again, not a particularly hospitable place to be 3 billion years from now. 4 billion years from now, our twin, the galactic neighbor Andromeda, which is moving towards us now at about 250,000 miles per hour, will have actually reached us. It will travel that distance of 2 million light years, and it will crash, if you like, merge with the Milky Way galaxy. There'll be spectacular tidal tails ripped out. Because space, galaxies, the space in between the stars is mostly empty, doesn't mean stars are naturally running into each other, but the gravitational influence is extreme. And what used to be two grand design spiral galaxies will merge into something that is more like a giant elliptical galaxy. So the sky will look very different 4 billion years from now, as the Milky Way, if you like, disappears to be just basically replaced with a spheroidal halo of stars that you can see sort of starting to take place there. 5 billion years from now, if we're still here, well, the sun will have run out of that hydrogen fuel that I talked about a few minutes ago. Nuclear fusion will cease. The star will move from the main sequence to the red giant. The atmosphere puffs up. If the Earth doesn't move, the best guess is it will be incinerated. Now, as the atmosphere of the sun is puffing up into the red giant phase, it's losing mass. And so as you start to lose mass, the planets can start to drift away. So there's, again, some debate as to whether the sun will lose enough mass quickly enough so that the orbit of the Earth will respond accordingly. And it may survive the atmosphere of the sun washing over it if it drifts out fast enough before that atmosphere reaches it. But in either case, we're not going to be living on the surface of the Earth 5 billion years from now. Be a very inhospitable place. 8 billion years from now, all of the residual heating in the sun will cease. It will end its life as a remnant called a white dwarf. It will crystallize likely over those few billion years into roughly an Earth-sized diamond. That'd be, if you want to work out using the current value of diamond, it would be about 1 billion trillion pounds. So it'll be enough to purchase the Earth 1 billion times over in terms of its GDP. So again, I'm sure someone in Elon Musk group is making a mental note of this for 8 billion years from now. And now the last view as I race forward now in time is jumping forward to 100 billion years from now. If somehow the Earth drifted out, or someone was able to push its orbit out so that we survive the red giant phase of the sun, if the Earth was still around 100 billion years from now, it's likely that its core will have cooled, but this is a really difficult geological measurement to do. But the Earth's core is cooling. Currently, we have a hot molten core. It's what drives our magnetic field. Why is it hot and liquid? Well, some of it is left over from the bombardment and the formation of the planet Earth, some of the heat that is trapped inside there. Some of it is the moon going around, which stretches and compresses and heats up the inner part of the core. And some of it is radioactive decay of things like potassium-40 and other isotopic unstable isotopes that provide the heat to keep it molten. But it is cooling all the time. And ballpark, you know, something like about 100 billion years from now, it will have cooled sufficiently that it will start to solidify. Best guess is that will take out the magnetic field. Surface radiation would increase by a factor of about 10,000 without that magnetic field. So again, having magnetic field is important for the development of life and the maintenance of life. And without that magnetic field, it would be the equivalent of more or less having a full body CT scan every day, is sort of to put that context of what the surface radiation would increase by. The other thing about 100 billion years from now is if you are an astronomer that happens to still be around, things are going to look a whole lot different. You know, we can currently take Hubble Space Telescope and do beautiful deep images of the sky like this, Hubble Deep Field and Ultra Deep Field, and you get this, you know, the incredible sea of galaxies appearing. 100 billion years from now, if HST is still limping along on battery and it does a nice dark image of what the sky looks like, it's going to look something like this. Not quite as spectacular as what you see on the left. And it's not down necessarily to stellar evolution changing things and the way galaxies look. It's simply the fact that, right back to where I started, the universe is accelerating. It's rapidly expanding. And so what happens is that because the universe is expanding, galaxies that we can currently see within our, what we call our light horizon, will expand beyond that cosmic light horizon. And a simple little cartoon, here's us in the middle of planet Earth, and there's two galaxies on either side. We can look back in time 13.7 billion years in this direction, and we can see this galaxy. We can look back 13.7 billion years over here and see this galaxy. Our observable universe encompasses both of those galaxies. But for this galaxy over here, you can look back in time 13.7 billion years and see us. But this galaxy is already outside of its observable universe, beyond its cosmic light horizon. As the universe is expanding and accelerating, galaxies drop further and further beyond that cosmic light horizon. And so in about 100 billion years from now, we're not going to be able to see any other galaxies. So the night sky for those deep images will look pretty boring. 1,000 billion years from now, star formation is still going on inside of the galaxy, but basically about 1,000 billion years from now, trillion years from now, we've used up all of the gas. There is no more. So there's no more new stars. There is just whatever is left over at that point in time is what you've got. And you leap forward 100,000 billion years from now, the last of those stars that formed will extinguish. So there will be no more nuclear fusion. There will be no more starlight. You'll still see remnant glows of the infrared of these stars as they are cooling down and cooling down, the remnants, the white dwarfs. But all that's left at that point in time is remnants, white dwarfs, and the remnants of exploding stars, black holes and neutron stars. So the universe is getting very, very dark in terms of optical light by that point in time. We leap forward 100 billion years. Those remnants that are left, the neutron stars, the white dwarfs, black holes, the vast majority of them, almost 100% of them, you know, in their standard orbits as they move around, occasionally they will come close to one another and they get a gravitational kick, a slingshot effect. It's called two-body scattering. So what happens is that 99% of the remnants that are left over in the galaxies eventually get shot out of the galaxy and sort of spread around the cosmos. Those few that are not ejected will fall into the supermassive black hole at the center of our galaxy, and what lurks at the center of effectively every galaxy. This just shows you the orbits of stars as they're going around the inner part of our galaxy, and we can infer that we have this 3 million solar mass supermassive black hole. So again, the majority of the remnants left over at that period of time get ejected, but on that time scale of 1,000 billion years, those few percent that are left over fall into that single supermassive black hole that's left over at the center of the galaxy. Going forward now, a billion years. What's left? The few little particles that are around, the things that we're made out of, protons and neutrons, are likely to have decayed. Now, free neutrons decay very quickly, 15 minutes or so. Free protons, it's speculated, we think they decay on that sort of time scale. So any other things that are left around that haven't fallen into these black holes will have gone. They will have evaporated, they will have decayed. The only thing left at that point in time are these black holes. And now going forward, you know, a crazy amount of time, billion, you can read off all of those billions right there. The only thing that are left, these black holes, they also decay. It's a very, very long time scale. It's through a process called Hawking radiation. And it's basically virtual particles that appear and disappear very quickly near the event horizon of a black hole. Some of those particles, if they, depending on when they appear and they disappear, they can appear and disappear and nothing changes. They can also appear, both fall into the event horizon, or they can appear, one of them falls in and one of them escapes. This is this is what Hawking radiation is, these occasional particles that escape. And this is what eats up the energy of the black hole and slowly causes it to evaporate through this process of Hawking radiation. And that's the sort of time scale that we predict that it takes for all of these remaining black holes, the only thing that's really left, to evaporate. And the only thing that is left at that point in time, black holes are gone, the only thing is left is these few little particles that have escaped. It's just a dilute gas of photons and what we call leptons, things like electrons. And the universe, again, remember, is continuing to expand and inflate exponentially. And all you're left with is this dilute gas of, if you like, photons and leptons cooling forever and ever and ever to lower and lower and lower energy. And this is basically how the energy ends. This is the universe ends. It's the final energy state. It's called the heat death of the universe. There's basically no way to take those leptons and photons and make anything out of them. We cannot extract energy from them to do anything with them. And so that is it. The universe just continues to expand forever with these photons and leptons and this ever increasingly lower and lower and lower energies on extremely long time scales. So there is no spectacular bang. This is how the universe ends, not with a bang, but with a whimper. So it's, in some sense, kind of a bit depressing. There are some potential ways around it, depending on what the nature of dark matter is and the nature of dark energy. But if we take those cosmic microwave background maps from the very beginning, everything that we can piece together today, this looks like how the universe is going to end, not with a bang, but with a whimper. But if I was going to end now, on a positive note, is that trying to answer these questions over the last few decades, has led to the development of some amazing technology that has obviously impacted on all of us. Probably almost everyone sitting here today is connected probably through the Wi-Fi. So the invention of Wi-Fi came about from Australian astronomers trying to look for evidence of these evaporating primordial black holes, not the big supermassive ones that I've just talked about, but one of Stephen Hawking's predictions of these primordial black holes left over from the Big Bang. Some of them should be evaporating today. Never found any evidence of them, but they came up with a very clever technique to allow them to sift through frequencies and lock on to particular frequencies. And that led to the development of Wi-Fi. The Australian government has the exclusive worldwide patent for Wi-Fi. If you don't know anything about that, go off and read the Wikipedia page. It's absolutely fascinating. And even things like the birth of the World Wide Web at CERN, those sorts of experiments that are aimed at answering the sorts of questions that we've just been talking about came about both at CERN and in Australia for these events. And that's just the tip of the iceberg. I did mention things like your GPS, your sat nav, they're anchored to supermassive black holes on the other side of the universe. So these esoteric topics of black holes, how they evaporate, their stability today underpins sat nav, GPS, Wi-Fi, the World Wide Web. So that's the positive to take from it, even though in a billion years from now, it may be a very depressing, cold, lonely end to the universe. Along the way, we've invented some pretty amazing things. So that is basically the sobering summary, if you like, is that the future is a little bit scary or a little bit depressing. And let me thank you very much for taking an hour out of your morning to listen to me. I appreciate it.
Thank you, Brad, for a fascinating talk. I'd certainly never thought of the the fact that the location of the solar system is kind of in the co-rotation radius for the Milky Way.
Yeah.
Another one of those little kind of makes you ponder for a minute.
Yeah, you don't like you if you take a whole lot of things that make it look like you're special. Not every planet has a magnetic field. We sit in just the right place. We've got a big moon that no other planet that we know of has. All these sorts of things. If you like to believe in the ubiquity of life, as I do, when you start stringing together a whole bunch of things that are a little bit rare, you do start to worry a little bit about that question of the ubiquity of life.
Yes, it's all those little things which you don't necessarily think about to begin with.
Quite.
I can see we already have 7 questions which have come in.
Yep.
For anyone who's sort of joined during the webinar, you can ask questions by typing the Q&A box. You see a button at the bottom of the screen. And also, just for a few people joined late into the webinar, we've got about 65 with us at the moment. And you will have this available on YouTube after the event, so you can always rewatch it if you missed the beginning. I'll also, just before going to the questions, just let people know that at 2:30 we have Dr. Andrea Font giving us a talk on stumbling in the dark, the search for the universe's missing mass. And then at 7 p.m. on Wednesday, the 16th of September, we have Nick James, the director of the Comet section, giving us a talk on Comet Neowise. I'll pick up the first of the questions. So we've got one from John Morrell. In the diagram of the open, flat, and closed universe, the triangles are shown on a plane, 2-dimensional universe, ignoring the curvature direction. In reality, should we think of this in 3 dimensions?
Yeah, the problem with so many cosmological analogies is working in the wrong sort of dimensions. We have a tendency to, you should be looking at these things in 3 dimensions. The classic example that one of the first examples I had about the expanding universe and why is everything moving away from us is, we use the balloon analogy as well. And, you draw little dots on the surface of your balloon, then you inflate it. It doesn't matter which dot you are standing on the surface of your balloon. As you stand there and look around you across the surface, every dot looks like it's moving away from you. So, this is fundamental to cosmology, that there's no special location. No matter which dot on that balloon I'm standing on, everything looks like it's moving away from us. So it works, it's a good analogy. It does sort of work. But every time I use that analogy, even with the youngest primary school kids, that immediately begs they can't make the transition from 3 dimensions into 2 dimensions, because I say, look, you have to pretend the universe is 2 dimensions. Because the first thing you do is you think, oh, well, what is that balloon expanding into? If I look up, that's outside the universe. And keep saying, oh no, the analogy only works in 2 dimensions. And you can't think of it in 3 dimensions. And I think the question that you've asked is a very fundamental problem that is endemic to a lot of the analogies that we use, is translating everything down to 2 dimensions from 3, or from space-time in 4 dimensions down to 3 dimensions. This trying to make it easy to wrap our head around means that you do sweep too much of the maths under the rug. So you have to be careful about getting that balance right.
Thank you. The next question we have is from Jack Martin, and he asks, what is the current estimate for the number of stars in our galaxy?
Yeah, that's a really good one. It's certainly, the number that I use, I threw the number 100 billion out there. It could be 300 billion. Wouldn't shock me. I think part of the issue is you can go out and count stars that you see today. But the low mass ones are a lot fainter and harder to pick up. And so there is still this debate, particularly for low mass stars that are a few tenths of the mass of the sun or half of the mass of the sun. It's hard to get a full accounting of those. We try it in different ways by looking at just doing star counts. We can do it by looking at even using the knowledge that we get from looking at other galaxies and measuring not the individual stars, but measuring the overall colors. Because even if you can't necessarily resolve these individual low mass stars because they're so faint, if you put a whole bunch of them together, they can provide a sufficient glow that you may pick out subtle differences in the colors depending on how many of these low mass stars are there. So there is, yeah, if someone came back to me tomorrow and said, actually, no, we think it's more like 250 billion stars, not 100 billion, I wouldn't be shocked. If someone said it's a trillion, I'd say, yeah, probably not. But I think that factor of few uncertainty in that 100 billion to 300 billion, sort of the right answer is probably in there somewhere, is the best I can probably say. I just use 100 billion because it's a nice round number.
Thank you. Next question is from Adam Fairhead, and he asks, we have seen red giants come to the end of their life, but have we ever seen a red giant form or forming out of the main sequence, or are the timescales too long and the events too rare or too far away to observe?
Yeah, it's more the, so yes, you can, statistically you can, if you look at a cluster of stars, say an open cluster, the stars, say an open cluster that was, say, the same age as our sun, say it's a 5 billion year, a cluster of stars formed 5 billion years ago. The high mass stars, they live fast, they die young, they've exploded as supernova, they've disappeared. Stars that are really low mass, less than the mass of the sun, look effectively the same as they did 5 billion years ago when they formed. So that main sequence is still there. But the stars that are around them, in that case, the mass of the sun, just a little bit heavier, 1.1 times the mass of the sun, those ones are starting to leave the main sequence and they're moving over to what's called the subgiant branch. And stars that are a little bit more than that, 1.15, 1.18, 1.2 solar masses, they're the ones that will be sitting on the giant branch now. So while you don't see an individual star making that motion, because it does take some time, it can take hundreds of few hundred million years up to a billion. It takes some time to move from the main sequence to the giant branch completely through the subgiant branch phase. But you can, in a statistical sense, you can pick out stars in that cluster that sit at each different point. So it's an individual star, but if you took the ensemble of them, you can kind of watch the evolution from the main sequence onto the giant branch. But there isn't that instantaneous point where you go, boom, it's gone from the main sequence onto the giant branch. You have to do it in a statistical sense and watch an ensemble of stars move their way through that. So yeah, that's a good point. Good question.
Thank you. The next question comes from an anonymous attendee.
Uh-oh.
WR104.
Yeah.
How did you arrive at the 7% or 1 in 15 chance?
Yeah, so hopefully I did the math right, because I did it very quickly on the back of an envelope. So I took the advice of the people who work in that field, who said that you had to, if you were within plus or minus 12 degrees, so you could think of a sphere and you've got a pole and you have plus or minus 12 degrees. So a cone, if you like, from the center, a cone upwards, which is 24 degrees across from side to side, if you like. So it just looks like an ice cream cone with a 24-degree opening inside of a big sphere. And so that cone can be pointing in any random direction inside of that sphere. So if you take a 24-degree opened ice cream cone inside of a sphere, that's roughly about it was 7% of the surface area of the sphere would be covered by that cone. So 93% would be missing, but 7% of the sphere would be covered by the 24-degree cone. So I hope that makes it very simple to draw it if I was drawing it, but that's where it came from, is just the opening angle, 24 degrees, as being the lethal cone angle, if you like, and that equals 7% or 1 in 15 of the entire sphere.
Thanks, Brad. Our next question is from David Gwynn. Do we have any evidence that our black hole at the centre of the Milky Way has been active? And what is the possibility of it becoming an active AGN in the future?
That is a really good question, and a very, very hot topic of conversation. I know that there are groups right now. I see on my Twitter feed things coming out just over the last few weeks, looking at exactly that. So yes, there is active, not active in the sense of being, I don't know, catastrophically active, but yes, there is evidence. We can see evidence of a bubble as you use more and more sophisticated X-ray telescopes and radio telescopes and gamma ray telescopes. We can map out that there is a bubble around it, and you can find it's not active in some sense right now, but we can see the imprint of the activity of that black hole, which is, I mean, we call it is supermassive in some sense, but it's still fairly small in the grand scheme of supermassive black holes. It's 1,000, 10,000 times smaller than the really big ones that we use to anchor GPS to, for example. So it's big relative to individual black holes left over from exploding stars, but very kind of piddly compared to the really supermassive black hole ones. But we do have clear evidence of these remnant bubbles that have been evacuated sort of around the center of the galaxy. It may not have had a huge impact on us out here or the outer part of the disk, but we can see evidence in the residual leftover X-ray and gamma ray maps that it has been active in the past, at least sufficient to leave that imprint, that fingerprint of activity. And I would encourage you, you could probably just Google this black hole Milky Way bubble, and you'll see very recent press releases just over the last couple of weeks talking about that exact subject. So yeah, very timely question.
Thank you. I can see we're still having a lot more questions coming in. Shall we say carry on for another 10 minutes?
I'm fine.
Yep.
As long as you guys are, yeah.
Cool. Well, what I'll do is I'll go on to questions, first of all, from people who haven't asked a question yet. So this one comes from Bob Shanks. Thanks, Brad. Great talk. Going back to the cosmic tug of war slide near the beginning, the pinch effect that narrows the tunnel caused by dark matter. Is this theory from our current understanding of dark matter, or is this observable somehow?
That's a good question, Bob. There probably is some latitude in the way that cartoon is drawn. What is clear is that there was a rapid expansion phase. I know the question that you're asking is, could you see the evidence of the slowing down, and then that transition from a dark matter dominated to a dark energy dominated dynamics of the universe. So what I can't remember off the top of my head, and perhaps it's something you could ask Andrea this afternoon, is whether it's kind of just a steady growth and then it quickly takes off, which is with the transition, whatever phase transition happens in the universe to go from dark matter dominated to dark energy dominated, whether you can see the pinching or whether that is a little bit of artistic latitude is not clear. What is clear is that there is something going at a certain rate and then it goes exponential. Whether you can see the little pinching and growth, I'd probably have to do a bit of hunting around to find out the answer to that one, but it's probably a good one to ask Andre as well. Good, yeah, it's a very good question, Bob.
Thanks. Now we have a question from Keith and Angela. Is it possible that the universe would expand only so far and then be pulled back together again, as though by an elastic band, and everything would collide and form another big bang, starting the whole process over?
That's certainly, when I was started my PhD back in Canada way back in the day, that was our favorite model. Was it looked like it was going to be finely balanced because we didn't really know about this dark energy and the acceleration. The just doing an accounting of everything that was out there, there was this, not a consensus, but a belief that there's a reasonable chance that we would have the gravity, if you like, would win out, everything would collapse, there would be a big crunch, and then potentially the cycle would begin again. What it looks like right now, at least if you take all of the observations and the evidence that exists right now with at least our current knowledge and understanding of dark energy and dark matter, is that it just doesn't look like that is going to happen. The way that I've sort of described this heat death of the universe, that's what the observations today look like. Now, we didn't really know didn't have a full appreciation of dark energy and its role 30 years ago, and so our picture of the universe changed a little bit, even though those were embedded within Einstein, as a solution to Einstein's equations, etc. But we didn't really know what the impact of that was going to be, and it changed our view of what cosmology was and the future of our universe was. Could something come? A little bit depends on the nature of dark energy. Again, this is one of the next Nobel Prize, well, next 2 Nobel Prizes, if you like, whoever can figure out exactly what dark matter is and figure out exactly what dark energy. We've already won Nobel Prizes for identifying the existence of dark energy, but actually pinning down exactly what the nature of that dark energy is will answer some of those questions, because there are, within the plethora of dark energy models that are out there, there are many different solutions that are consistent with probably what I just described now. The heat death of the universe is probably the more or less accepted version of how things are going to go. But if something about the nature of dark energy, if there is another phase transition and something changes, then maybe that's difficult to predict. And so maybe what I've just described won't work. There's still some who believe that there will be a big rip. Everything I just described doesn't work out. In the big rip model, where everything just expands exponentially, and that exponential expansion just grows exponentially, if you like. Dark energy just wins out at all scales. What happens is basically galaxies fly apart, individual atoms fly apart, dark energy rips apart everything, and it does it on a time scale of only 20 to 25 billion years or so. So very, compared to the sorts of scales that I was talking about, that would happen. That's not the same as obviously collapsing and reforming another universe, if you like, through a big crunch. That would just be the end of the universe even quicker. But again, that got a lot of attention, a lot of press coverage, a few years ago, and you can Google Big Rip. There's an entire Wikipedia page about it. But again, most of the observational evidence is now against that Big Rip model, and the more slow, lingering end of the universe with a whimper model seems to be what the observations are consistent with right now.
Thank you. The next one is questions from Graham Roberts, and is, what is the current thinking that we are part of a multiverse world, and how would this impact on your projected outlook for our universe?
Yeah, I think that's a great question. I'm going to pull up this. Where is it? Let's pull up this one again. So right now, it's also a fascinating read. So I'm not trying to push everyone to go off and look at Wikipedia, but if you look at the multiverse model of cosmology on Wikipedia, there's, towards the end of that page somewhere, if I'm going by memory, they've got a breakdown of scientists who believe in the support the multiverse theory and scientists who do not support it. And it's not filled with crackpot scientists. There is more or less this equal split with highly respected scientists in both camps. And I guess the short answer is it's beautiful, elegant maths with absolutely no way to test it experimentally. That's maybe somewhat flippant, but that captures the essence of it. So the theory does allow for multiple universes, but it also doesn't provide any physical experimental way to test whether it is, you know, valid or not. So in some sense, it's, again, beautiful mathematics, but also somewhat philosophical in some sense. Now, the reason I pulled this up was that a number of years ago, people had commented on things like, I can't remember if it was, actually, I think it was one of these ones over here. It might even be this one over here. These cold spots. I mean, again, relatively cold. It might be 2.69998 degrees rather than 2.7000. But one of these spots had been claimed as being potentially evidence of another universe sort of pushing into ours. Now, we look back now and with more observational data and realize that those sorts of cold spots do exist. When you go to higher resolution data, they don't become gigantic. They sort of, you know, break up into more mottled pattern that you see elsewhere. And it's probably it is just a statistical, not anomaly, but you do get cold spots and you do get hot spots. It did get a lot of attention, and every couple of years or so, it gets pulled out again as being, you know, the cold spots that you see are potential evidence of universes impinging on us. So I think ultimately I don't think it impacts on what I've just described here in our particular universe. It is a very good question. So, but ultimately, I think it's what I've just described is independent of the multiverse theory. Even though I think it's fascinating, but it's, you know, the maths involved in the multiverse theory is way above my head. This is the realm of sort of the Stephen Hawking's of the world. But right now, doesn't seem to be there's no observational evidence to support it. Conversely, there's no observational evidence to refute it.
Thank you. Shall we have one final question? Which this one is from Olaf, and it's Homo sapiens as a species have been around for a little under 1 million years. Are we assuming that environmental pressure to evolve biologically in intelligence will no longer apply over millions of years in future?
Well, I mean, that's a great question. Again, bordering on, you know, it's biology, it's philosophy, it's theology. I mean, I don't have a good answer to that, because I think you know, what direction evolution will take in terms of our biological development over, you know, 'cause as you say, it's, you know, on that timeline, you know, Homo sapiens have been around a few 100 million years. It's a drop in the bucket in the grand scheme of things, and we've gone from you know, even from single cell to multi-cell to mammals to Homo sapiens in a very short period of time. And, you know, what does the next, you know, if we did that in a few 100 million years, at least transitioning from mammals to Homo sapiens, you know, arrival of Homo sapiens, you know, that's, again, it's like you say, it's a very short period of time, 1 million years. What will things look like in 1 million years from now? Yeah, I mean, I don't know. I read as much science fiction as the next person and can speculate wildly, but I really don't know. But one would imagine if we've had a lot of rapid changes on a relatively short time scale, at least on the geological and astronomical time scales, you know, is there any reason to think that we're just going to all of a sudden just stop for the next million, 10 million, 100 billion, however long you want to go? Seems unlikely. But yeah, again, I think that's more speculative than I have the ability to speculate upon.
Well, thank you very much, and thanks for trying to answer what is inevitably a very difficult question. And thanks for the fascinating talk and spending the time answering.
I appreciate it very much. I was glad to fill in. Christine, is a great speaker, and it's a shame she couldn't been here, but it was great chatting with you all, and I hope that we can do it again face to face in a post-COVID-19 world.